So right back in this series of videos, we defined the voltage across the capacitor as being the voltage going in multiplied by 1 minus e to the minus t over RC. But where does this equation come from? That's an important derivation that you might be asked to find. Obviously, t equation is given in the time domain. RC is this RC time constant that we defined tau, that's in seconds. What we can begin to do is if we think about the equations, the Kirchhoff's voltage law equations in the time domain, and we then consider them in the frequency domain or the S domain by doing a Laplace transform, we can manipulate the differential equation quite easily through the use of algebra, and then if we do an inverse Laplace transform, we can begin to derive this VC. So if we consider what this voltage mesh would look like in the S domain, the V of t, this would, if we took the Laplace transform of that, we end up with V sub s over s. And then we have the R IT. If we take the Laplace of that, we end up with R IS. And then if we have this capacitance here, the capacitance, if we take the Laplace of the capacitor, we end up with 1 over SC. If we express now this mesh as V, then we can take the IS out. So what we can then say, we bring this down to the bottom here, like so. If we multiply top and bottom by 1 over R, we will end up with, basically then, multiply this through, this S by this and this by this, those S's would cancel, so we'd end up with S plus 1 over CR. So we could rewrite that. This is a constant V sub s over R, and if we take the inverse Laplace transform, so we're going to transform this now back into the time domain, I sub s becomes I of t. We have, that's still a constant, so the inverse Laplace of 1 over s plus alpha, so if we look at our Laplace tables, 1 over s plus this alpha transforms, so this is the Laplace transform of this. So this is our alpha here, this is our s plus, so we can write that as, we can see then we've transformed from this S domain, we've derived the time domain version, so this IT here, we've derived it, and we can see that when t equals 0, then this would equate to 1, so this current is therefore at our maximum, which is what we'd expect to see. So we'd see this maximum current here, and this is proportional to our V divided by R. That's why it's really important to have this R in there. And the time constant is the discharge time or the charge time, whichever way you want to look at it. And therefore, if we look at what the voltage is across this resistor, we can define that simply as our R times I. So we can say that the VRT So that there is the equation for the voltage across the resistor. Well, if we know, because of Kirchhoff's, we know that we've got the total V must equal this plus this one. So therefore we can see that the VC time must equal, that is where that equation comes from. This equation here, same as this equation here.